Today we will see in detail the spin-off particle and Pauli matrices. This is a revised version. Earlier I have given same lecture with a lot of mathematics, which I have removed it now. Uh, Here in this lecture, unlike previous lecture, here I am using the Dirac notation. So from this lecture, you can understand the power of the Dirac notation, how simple it is for derivation purpose. Uh, so we will proceed with the Dirac notation. The algebraic theory of spin is a carbon copy of the theory of orbital angular momentum or total angular momentum, whatever may be, beginning with the following fundamental communication relation. Remember that whether it is orbital angular momentum or total angular momentum, L or J, or spin orbital momentum, whatever may be, these three comes under Lie algebra. Lie group, that is Lie group means whatever applicable for one Lie group is applicable for other Lie group too. Say for example here, the commutation of H comma Sy is equal to IH cross SZ. This is equally valid for orbital angular momentum L or total angular momentum J. Say for example Lx commutation of Lx with Ly is equal to IH cross Lz. In that way, because these three are in comes under Lie group. Similarly, Sy Sz is equal to IH cross Sh. Similarly, the commutation of Sz uh, with Sh is equal to IH cross Sy. Generally, it can be written as where I comma j is equal to xyz. That is commutation of I with sj is equal to IH cross epsilon ijk sk. That is this epsilon ijk is 0 if any two of these parameter is equal, and it is plus 1 if it is clockwise direction cyclic. If it is anti-clockwise, then it is minus 1. So this is also valid for orbital angular momentum L and total angular momentum J. As I said, it comes under Lie group. The spin operators become 2 by 2 matrices, which we can work out by noting their effect on alpha and beta. Here alpha is the spin up, represents spin up, and beta represents spin down. When S squared act on alpha, you will get an eigenvalue of S into S plus 1 H cross squared and alpha. Uh, like you remember that when L squared act on the wave function, the eigenvalue is L into L plus 1 H cross squared. Similarly, for J squared, the eigenvalue is J into J plus 1 H cross squared. In that way, you will get S into S plus 1 H cross squared alpha, because all forms a Lie group, which is equal to spin is off. So half into half plus 1 into H cross squared alpha. So if you add these two, you will get 3 by 2. Here 1 half. So this will become 3 by 4 H cross squared alpha. Similarly, when S square act on beta, you will get 3 in same method. You will get 3 by 4 H cross squared beta. Now we will see about the S square matrix. Now we have seen when S square act on alpha, we will get an eigenvalue of 3 by 4 H cross squared, and this alpha. Similarly, for S squared beta is equal to 3 by 4 H cross squared beta. Just now we have seen this. If we write this in the matrix form, uh, uh, you know very well that bra vector is row vector. So first you take alpha, bra alpha with here also next bra alpha, because it's a row matrix. and we are using operator s squared. So this is alpha s squared alpha. Remember that this is get alpha. Get vector is a column vector. So you can see alpha alpha. Similarly here beta beta. So which act on s squared. Similarly here the row is beta. So the bra vector is beta, that is rho is beta, and here the get vector is column vector alpha. Here column vector is beta. So we are acting the get vector over s squared. So you know when s squared act on alpha or beta, you will get the eigenvalue of 3 by 4 h cross square. That we are taking out. Now here when s square operate on alpha, you have taken the eigenvalue out. So this become the inner product of alpha with alpha, which is equal to 1 here. Similarly here the inner product of alpha with beta, because when the s square act on beta also, you will get 3 by 4 h cross square eigenvalue. So alpha with beta is 0. Similarly here beta with alpha, which is also 0. Here you can see beta with beta is 1. So you will get 3 by 4 h cross square 1 0 0 1. We have seen S squared matrix. Now we will see H Z matrix. When H Z act on get alpha, what you will get? Half H cross. That is when LZ act on any get vector, you will get an eigenvalue of M H cross. Here M is the magnetic momentum. Here only we have two value, plus of or minus of. So when Sz act on alpha, you will get an eigenvalue of H cross and get vector alpha. When it act on Lz, you will get MH cross, or Jz, you will get MH cross. Similarly, when Sz act on get beta, you will get minus half H cross get beta. So in the matrix form, alpha is row matrix because it's a bra vector. Then here the get alpha is a column vector. Here get beta is column vector. Here beta is row vector. So you can write the matrix alpha hz alpha, alpha hz beta, beta hz alpha, beta hz beta. Now you substitute from here. When H act on alpha, you will get half H cross. Half H cross I am taking out. So the first one will become inner product of alpha with alpha, which is equal to 1. Similarly, the second one, alpha inner product of alpha with beta, which is equal to 0. Similarly, this one, beta inner product of beta with alpha is equal to 0. Here you can see when Sz act on beta, you will get minus half H cross. Already you have taken half H cross outside. Here the minus negative sign remains. So negative sign beta with beta is 1. So this will become minus 1. So Sz matrix is half H cross 1 0 0 minus 1. So we have seen the HZ matrix. Similarly, we have to find the uh, SH matrix and the SY matrix. For that, we should know about S plus. Here, this is the rising operator. You know very well. L plus is rising operator in an orbital angular momentum, and J plus is rising operator in the case of total angular momentum. Likewise, this is S plus. When S plus act on alpha, alpha is spin up. Already it is upward spin, so you cannot rise beyond that. So when S plus act on alpha, you will get 0 naturally. The eigenvalue will be 0. When HZ act on beta, this is lower. So spin down will become spin up. So this will become H cross alpha. So in the matrix form, I need not explain again and again. So you can write alpha s plus alpha, alpha s plus beta, beta s plus alpha, beta s plus beta. Now, when s plus act on alpha, here you can see the column will become 0 because s plus act on alpha, that is spin up get, so it will be 0, column will be 0 naturally. When s plus act on beta, what is that here? H cross eigenvalue. So you will take H cross, then you will get here H cross alpha with alpha. Remember that you will, when s plus act on beta, you will get H cross alpha alpha. So this is alpha with alpha, which is equal to what? H cross, I have taken it out. This is H cross, this is alpha. Remember that you will get H cross alpha when s plus act on beta. So this is beta, inner product of beta with alpha, which is equal to 0. So then naturally s plus will be H cross 0 1 0 0. Similarly, we have to find S minus matrix. This is lowering operator. So when S minus act on alpha, alpha is spin up. So naturally it will get spin down, H cross beta. Similarly, when lowering operator operate on beta, that is already it is in the lower state, that is spin down. So the eigenvalue will be 0. So usual matrix form, this is alpha s minus alpha, alpha s minus beta, beta s minus alpha, beta s minus beta. So when lowering operator act on beta, you will get 0. So this column will become 0 0. Here you will get beta. Remember that you will get beta. So this will become H cross alpha with the beta. This is H cross beta with beta. So the inner product of alpha with beta will be 0. The inner product of beta with beta is equal to 1. So I have taken this H cross out. So now the S minus matrix is equal to H cross 0 0 1 0. Actually, our aim is to find Sx matrix and Sy matrix. Uh, this is our S plus matrix, that is H cross 0 1 0 0. S minus matrix is H cross 0 0 1 0. Just now we have seen. We know already S plus is equal to Sx plus Isy, and S minus is equal to Sx minus Isy. You remember that the same thing will happen for orbital angular momentum, that is L plus is equal to Lx plus Ily. Same thing for J. So now how to find the Sx? You add these two, S plus and S minus. So naturally this minus ISY plus ISY will cancel with each other. So Sx plus here one Sx, so you will get 2 Sx. 2 Sx is equal to S plus plus S minus. So this 2 will come here. So this will become half S plus plus S minus. Uh, so what will happen if you add these two matrices? Here you can see H cross. So H cross here the first row second column is sorry, second row first column is 1, and second row first column is 1. So this is 1, that is first row second column, and second row first column is 1. Here 0 1. So if you add these two, you will get 0 1 1 0. Of course there is a H cross, here you have 2. So this Sx matrix will be H cross over 2 into this matrix 0 1 1 0. So the S plus matrix is H cross 0 1 0 0. S minus matrix is H cross 0 0 1 0. And this also we have seen S plus is equal to Sx plus Isy, and S minus is equal to Sx minus I Sy. Now you subtract this S plus with minus S minus. What will happen? This Sx will go away. Then here you have Sy. Here I minus, you are subtracting this. So minus of minus I will become plus. So you will get 2Iy. So this will become, if you bring 2I right hand side, then you will get Sy is equal to 1 over 2I S plus minus S minus. So just you substitute this. First S plus is 0 1 0 0. You are adding this with sorry, you are subtracting this S plus matrix with the S minus matrix. So this 1 will become minus 1. So outside the matrix you have H cross by 2I. Now you multiply and divide by I. So you will get IH cross divided by 2I squared. I squared will become minus 1. So this. Now you bring this minus I inside the matrix. So this will become 1 will become minus I. This minus 1 will become plus I. So SY matrix is H cross over 2 0 minus I 0. So this is SY matrix. So we have seen the S squared matrix is 3 by 4 H cross squared 1 0 0 1, and Sx is equal to H cross over 2 0 1 1 0, and Sy is equal to H cross 2 0 minus I 0, and Sz is equal to H cross uh, H cross by 2 1 0 0 1. These are the four matrices. If you have seen my earlier lecture about spin-off particle and Pauli matrices, now by this time you should have realized how tedious that my previous lecture was. Of course, I have removed it now. Now you can understand how simply I have done the same thing using Dirac notation. That is the power of the Dirac notation. Here I like to highlight one more important point. It is conventional to define the dimensionless version of Sx, Sy, Hz as Pauli spin matrices. We have seen Sx is H cross by 2, 0, 1, 1, 0. Uh, so that can be written as sigma x is equal to 0, 1, 1, 0. We have removed this H cross by 2. Here also we have removed H cross by 2. So sigma y is equal to 0 minus I 0. Similarly, Hz, we have removed H cross by 2. So we'll get 1 0 0 1. Here one interesting phenomena about all these matrices are, you can see the trace here 0, here 0, here also 0. So polyspin matrices are spinless. We will see some more property now. These are the following important properties of Pauli spin matrices. Is proof is very simple and straightforward. So I am not going to do that. They anti-commute each other. Spin matrices anti-commute each other, and sigma x sigma y is equal to I sigma z, and it is a cyclic permutation. As I said, a trace of any Pauli spin matrix is, that is sigma I is equal to 0, and determinant of any Pauli matrices is minus 1, and square of any Pauli matrices is unit matrix. This is anti-commutation relation. That is, when sigma I anti-commit with the sigma j, you will get 2 delta ij. This is Kronecker delta ij. When I equal to j, it is 1, otherwise it is equal to 0, then I unit matrix. 2 times delta ij unit matrix. Similarly, this is anti-commutation relation. Then commutation relation sigma I sigma j is equal to 2i epsilon ijk sigma k. You know the meaning of it. If any two of these running index is same, then it will be 0. If it is in clockwise direction, it is 1. If it is anti-clockwise direction, it is -1. Similarly, the trace of the product of sigma I into sigma j is equal to 2 times delta ij, where this delta is Kronecker delta. So this is equal to 1 when I equal to j, otherwise it is equal to 0. These are the some of the properties of Pauli spin matrices. Thank you very much for watching my videos and supporting me continuously. Kindly subscribe my channel, that is youtube.com/c/vasuv physics. Thank you very much.